the strangest, the most extraordinary, the most impossible phenomenon in the entire universe. Something that shatters every law of physics. What is it?
Black holes. Truly, they are at the heart of the biggest, most heated debates in all of physics, in all of science.
Let's go back to Newton's time first. After he proposed the universal law of gravitation, naturally, everyone was talking about it.
Different scientists interpreting this law kept arriving at the same conclusion. The more massive an object, the stronger its gravitational pull.
That meant anything trying to escape from such a massive object would need to move much, much faster. So what happens if an object has a mass that pushes the limits of imagination? Say tens of times more massive than our sun?
Not even light could escape.
And that was our very first hypothesis about black holes, roughly 400 years ago, a dark star. Not a bad guess, actually. For its time, it was remarkably accurate.
They just had no idea what would actually happen when an object became that massive.
Because no matter how you looked at it, something from which not even light could escape was simply unacceptable. A thing that traps light itself? For a very long time, many physicists, even the greatest names in science, believed it was simply impossible.
But the real debates were about to begin, roughly 100 years ago, with another revolution in physics.
With the name behind that revolution, of course, Albert Einstein. Hello again, Mr. Albert.
With his general theory of relativity, Einstein changed everything. You already know this. We've talked about it extensively in our What is Time and Space is Not Empty videos. He spoke of space-time and how the universe has a fabric. The more massive an object, the more it warps that fabric.
Massive objects would bend everything. Even time itself warps, and at some point, time could stop altogether. Stopping time. But we'll get to that.
Now, building on this revolutionary theory, German physicist Karl Schwarzschild arrived at a truly mind-bending conclusion. If you keep an object's mass the same, but shrink its size as much as possible, as far as atoms will allow, the density increases beyond belief, and the warping of space-time increases right along with it. Let me give you an example. Take our sun. If you compress the sun down to just 3 kilometers across, or squeeze the entire Earth to 9 millimeters, small enough to fit inside a standard bullet, this is what would happen. This isn't just any ordinary warping. The density reaches a point where space-time can bend all the way to infinity. Infinity. In truth, infinity is just a reflection of the limits of our own understanding. When Earth is compressed to 9 millimeters, the object warps space-time so severely that light cannot escape, meaning we cannot see it. We called this density threshold where light becomes trapped the event horizon, and that is the origin of the black hole concept. But despite all these hypotheses, despite the support of the mathematics, nobody believed such a thing could actually exist in our universe. After all, it completely destroyed the laws of physics as we knew them. But then, a relatively unknown name, a 19-year-old from India, a young genius named Subrahmanyan Chandrasekhar, had something to say about all of this. His work on the internal structure of stars earned him a place at Cambridge University, and in the 1930s, his research on white dwarfs would light a spark that changed everything. We talked about white dwarfs in our dark energy video. We described them as what remains after a star exhausts its nuclear fuel and dies. But there's a limit to how small these stars can shrink. The star sheds some of its mass in a kind of explosion, and the remaining matter compresses into a small, incredibly dense stellar remnant. There's a reason for this limit. Atoms only allow matter to be compressed so far. A white dwarf can be the size of Earth but carry the mass of our Sun. Imagine a single sugar cube weighing several tons.
While Chandrasekhar was conducting his research in England, everyone believed that all stars ended their lives as white dwarfs. That was the final chapter, because everyone accepted there was a limit to how much atoms could be compressed.
But Chandrasekhar's calculations were telling a very different story. They showed that once white dwarfs exceeded a certain mass threshold, they would continue to collapse, shrinking toward infinity.
Previously, scientists believed a star could only shrink to a minimum diameter of about 10,000 kilometers. But Chandrasekhar discovered that a star roughly 1.4 times the mass of our Sun would be unable to resist its own gravity. It would continue collapsing toward infinity.
And that, in its simplest form, is the definition of a black hole.
But of course, these findings were met with fierce resistance from the scientific community, especially from another name at Cambridge at the time, Sir Arthur Eddington, who came down particularly hard on the young physicist. You remember Eddington, one of Einstein's biggest supporters, the man who proved general relativity during a solar eclipse. But even for him, this idea was too wild.
Let's say a star shrinks to a few kilometers. Fine, no problem. But beyond that, collapsing to infinity the way you describe, that is in the simplest terms absurd, he would declare.
After this, Chandrasekhar would continue his work in America. And during this period, a wild new discovery in physics would once again strengthen his claims.
It was already known that atomic nuclei consisted of protons and neutrons, with electrons orbiting around them. But in 1932, a groundbreaking discovery revealed that, under extreme compression, electrons and protons could merge together to form a structure made entirely of neutrons.
And it would be theoretically proven that this neutron matter could compress even further. A star with more than 1.4 times the mass of our Sun would undergo a massive explosion and transform into one of the most extreme structures in the universe, a neutron star.
Just like the neutron star inside the Crab Nebula, the star at the center of that nebula is a neutron star.
Remember, we said a sugar cube from a white dwarf could weigh several tons. Now imagine a sugar cube from a neutron star weighing hundreds of millions of tons.
So now we knew a dying star wouldn't necessarily stop at the white dwarf stage. There was something beyond, neutron stars. But once again, resistance formed. Everyone now declared that a neutron star was the absolute final stage a star could reach. Beyond that, impossible.
And here, a very different voice would rise. One of the most brilliant, most controversial, most loved, or most hated scientists in all of history. J. Robert Oppenheimer.
Oppenheimer, the Manhattan Project, atomic bombs, and so much more. We'll have a lot to say about him, but let's not get sidetracked for now.
Oppenheimer would run his own calculations on this matter, and he would find that a star with 3 times the mass of our Sun would not stop at the neutron star stage when it dies. It would keep collapsing.
But the debates were far from over. Another famous name, John Wheeler, would push back against Oppenheimer. He argued that as a star loses mass and shrinks to around the size of our Sun, it would collapse and end up as either a neutron star or a white dwarf. Anything beyond that, he said, was meaningless.
Nobody could accept that something this strange could actually exist. But like any good scientist, Wheeler kept working on it. He wanted to prove why it couldn't happen.
And here's the irony. John Wheeler, the man trying to disprove them, is the very person who gave them their name, Black Hole.
But the deeper Wheeler dug, the more he got lost in it. He threw everything at it. General relativity, gravity, space-time. He added, he subtracted. Nothing worked. Every calculation on his journey to prove black holes impossible pointed to one single conclusion. Black holes could exist. In fact, they had to exist. There was no other explanation.
The dream of a 19-year-old who set out from India, Chandrasekhar's vision, had come true.
The year delivered with significance, dignified and respectful triumph. And though many years would pass, his tireless efforts would finally be recognized. In 1983, Chandrasekhar received the Nobel Prize in Physics.
So finally, the existence of black holes was an undeniable fact. We even knew how they form. We had a complete recipe. But something was still missing.
An actual black hole. Proof. We had no image, no observation, nothing to prove they actually existed out there.
A new adventure lay ahead, a challenge to find the first black hole.
It became every scientist's dream to find the phenomenon that was once thought impossible, to prove it was real.
But that is a story for another time. Another story of triumph.
Black holes. We said at the beginning they were among the strangest things in the universe, but they're not just mysterious monsters sitting out there in the dark. They would open entirely new doors for us and offer answers to questions we couldn't solve any other way.
Are black holes really black? Are black holes really holes?
And there's more. You know the most important question in all of science, don't you? The greatest mystery. The question everyone is trying to answer right now.
The gap between quantum physics and general relativity. The theory that will connect these two revolutionary pillars of understanding.
The theory of everything.
And black holes may hold the answer to even this. In fact, they've already given us many answers.
Thanks to a name as important as Newton, as important as Einstein, someone we've barely mentioned until now, Stephen Hawking.
On this long journey we've been taking together, the time has finally come to talk about him and his extraordinary genius. Not just one video, but several. I can't even predict how many. We'll be spending a lot of time with Stephen Hawking from now on.
But first, how about we find the first black hole together in the next video? Let's not waste any time. After all, Oppenheimer's waiting for us too, isn't he?
Before we go, for videos like this to keep coming, for science to stay popular, for more people to join the conversation, and for Science Mosaic to keep going, I'm counting on your support through Patreon and the join button. As I've said before, every video I've made and will make stays free for everyone, but your support means the world. But no matter what, as I always say, until we meet again, I'm so glad you're here.